Okay, today we're going to look at quadratic equations again, and we're going to look at their graphs and see what properties of the graphs we can actually figure out and how to find certain parts of the graph. In the last chapter, we did something like f of x equals x minus 2 squared plus 5. And we know now that, well, if I want to graph that, this is a regular parabola. It's shifted 2 to the right and 5 up. So 2 to the right, 5 up. And if I graph it, it'll look like that, and we're done. We can label this 0.25 if we want. Which essentially means that as far as it goes, for the parabola, all I really need to know is where this point is, where the vertex is, and then I just draw my u or my n, I suppose, if it's upside down, and I'm done. So now we want to see if there's some way we can look at a regular quadratic in standard form and find that point. So, suppose we have f of x equals 2x squared plus 4x plus 3. I want to graph that quadratic. There are different ways to do it. One of them is to say, well, if I can put it in vertex form, the other form I had it in where I can see the transformations, well, then I can graph it. So we could do that. And we could say, well, in order to do that, you need a trick. We've used it before, completing a square. So let's see. We're going to complete the square on this. In order to do that, I care about the quadratic term and the linear term. I need the leading term to be 1. It's 2, so I factor that out. So I get 2 times x squared plus 2x plus 3. Now complete the square on this stuff right in here. Let's see. To complete the square, I take half of the linear term, half of 2 is 1, square that and you get 1. But then the rule is, whatever you add here, you have to subtract off. You could add it to the left and then subtract it back over if you want to. You don't have to. We're just going to subtract it off. But keep in mind here, I added 1 in here, but there's a 2 out in front, which means technically I didn't add 1, I actually added 2. So since I add 2, I subtract 2. And now this becomes 2 times, let's see, we want to factor that because it's a perfect square. And it'll just factor to x plus 1 squared plus 3 minus 2, which is 1. And now from there, well, I could graph it pretty easily. Let's see, that's a regular quadratic, stretched vertically, shifted 1 to the left and 1 up. So maybe it's right here, and it goes up like that. Negative 1, 1. So if we want to graph these things and they're in standard form, one thing you can do is do the algebra out to complete the square, get the vertex that way, find your transformations, and then you're done. But there is actually a shortcut you can use, and I'm not going to take the time to develop the formula out because, honestly, if you guys are watching this video and I did all that, you just fast forward through it anyway. So I'm not going to bother doing it out. I'll give you the formula, and then we'll see that it actually works and why. And all it is, and I want to leave all this up here so we can see it. For this quadratic right here, we know that's in standard form, ax squared plus bx plus c. And now for the vertex, the x value of your vertex is negative b over 2a, which in this case is negative the b value, which is 4, over 2 times the a value, which is 2. So I get negative 4 over 4, which is negative 1, which is the exact same x value I got over here, completing the square. Once you have the x value, take that x value, plug it into your function, f of negative 1. That will tell you the y value of the vertex. So for this one, we'll get 2 times negative 1 squared plus 4 times negative 1 plus 3. Negative 1 squared is 1. 1 times 2 is 2. 4 times negative 1 is negative 4. 2 minus 4 is negative 2. Negative 2 plus 3 is 3 minus 2, 1. So this simple little formula, x equals negative b over 2a, tells me the x value of my vertex, and then I plug that in and get my y, and I'm done. The vertex is at negative 1, 1, which I knew here. Again, there's actually an algebraic reason that this works. It's in your book, and I know if I just do it on the video, none of you will watch it, so I'll just alleviate doing that. The short version of it is, if you want to graph a quadratic in standard form like this, you have two options. You can either do the algebra and complete the square, put it in vertex form, because then you can just read the vertex off, negative 1, 1, like we did over there. Or use this shortcut. The x value of your vertex is negative b over 2a, as long as it's in standard form. Plug in b and a, get the x value of your vertex, take that, plug it into your function, find the y value, and you're done. So maybe one more example and then an application just so we can see this in action. So suppose we have f of x equals negative 2x squared plus 8x minus 5. I want to graph that. Well, find the x value. According to what we just did, it's equal to negative b over 2a. So that's negative the b value, which is 8, over 2 times the a value, which is negative 2. Two negatives cancel, become positive, and then you get 8 over 2 times 2, which is 4. 8 over 4 is 2. That's the x value. To find the y value, just plug 2 in. So we get f of 2, which is negative 2 times 2 squared, plus 8 times 2 minus 5. Let's see, 2 squared is 4. 4 times negative 2 is negative 8. 8 times 2 is 16. And we get negative 8 plus 16, which is 16 minus 8, 8. 8 minus 5 is 3. And there's my vertex, 2, 3. If I wanted to graph it, well, let's see, 2, 3. We'll say it's right here. And now we just draw the parabola. The only problem is, well, I guess my parabola could look like this and go upwards, or it could also look like this and go downwards. And just knowing what the vertex is doesn't tell me if it opens up or opens down. We need one other trick for that, and the trick is, just look at the leading coefficient, the a term. If that's positive, it'll open up. If that's negative, it'll open down. In this case, it's a negative 2, so it'll open down. So my graph goes downwards. And it looks like that, the parabola reflected across the axis. Pretty straightforward, pretty simple. Keep in mind, you're only going to be able to do this if you remember the formula. X is equal to negative b over 2a. That tells you your vertex, and once you have that, the leading coefficient tells you if it opens up or opens down. One quick application, because these occur a lot in the real world. Let's see. I throw a ball straight up. We have done projectile motion equations before, so these are pretty standard. And let's see, I throw a ball straight up. Its height at time t is given by h of t equals negative 16t squared plus 80t plus 5. When does it reach its maximum height? So I throw a ball straight up. Its height at time t is given by h of t equals negative 16t squared plus 80t plus 5. When does it reach its maximum height? This is called an optimization problem. You want to find the biggest value or the smallest value, the maximum for this one. So think about the graph. That's a quadratic, which means it tells us it's a parabola. And we know since the leading coefficient is negative, it's a parabola that's reflected that opens down. Which means the graph is going to look something like this. Where on that graph do you get a maximum? Well, right here, right at the vertex. So now, to find when it reaches its maximum height, we just need to find the vertex. So just use a formula. Let's see, x, or in this case it's t, but I'm just writing x as a standard. X is equal to negative b over 2a. So it's negative b, which is 80, all over 2 times a, which is negative 16. The two negatives cancel, and you get 80 over 16 times 2, which is 32. And then if you want to throw it into your calculator, 80 divided by 32 is 2.5. So it reaches its maximum height in 2.5 seconds. A follow-up question you could ask is, what is the maximum height it reaches? But if this time equal to 2.5 is when it reaches its maximum height, to find the maximum height, just plug in 2.5. So you would just take h of 2.5 equals negative 16 times 2.5 squared plus 80 times 2.5 plus 5. And then really quickly, let's see, 80 times 2.5 is 200. 2.5 squared times negative 16 is negative 100. And you get 200 minus 100, which is 100 plus 5, 105 feet. That's all calculator work. You guys can throw it in and solve it. But essentially the point is, we'll be solving applications with these quadratics. As soon as you see find the maximum, find the minimum, whether you're talking about projectile motion, economics, cost, revenue, profit, things like that, as soon as it's a quadratic and you're trying to find its maximum or minimum, just find the vertex. Negative b over 2a gets you x. And if they want to find y, plug in the x and get y and you're done. They're pretty much the most straightforward applications you can do. So that's it. Next time we're going to deal with some more algebra similar to this.